Hi, I'm Shuan. Now I'll introduce you to Pipy. It's a programmable proxy software our team created for the cloud, edge, and Internet of Things. We call it a programmable proxy because fundamentally it's a script engine executing a JavaScript-esque script language we call PipyJS. PipyJS is a tailored version of the standard JavaScript language. We removed all the object-oriented programming stuff, that is, the prototype system, only keep its functional programming parts. Then we combine it with a very unique API based on pipelines and filters to make Pipy an extremely flexible network programming engine for various networking tasks. Pipy is written in C++. It leverages asynchronous network I/O. Allocated resources are pulled and reused. Data is transferred internally by pointers whenever possible. It's fast in every way. A build of Pipy with no built-in GUI resources gives you an executable merely around 10 megabytes with zero external dependencies. You'll experience the fastest download and startup times with Pipy. Now let me show you some examples so you can see how it works. The first example is a simple HTTP server. But before that, I want to show you real quick how Pipy in itself is just a script engine that evaluates JS expressions. So if I say Pipy-E 1 plus 1, it tells me 2, because 1 plus 1 is a valid expression. So Pipy evaluates that expression and gives the answer 2, just that simple. So to start a simple HTTP server, we should use an expression that after evaluation we get a configuration object. That configuration is for the server. So first, we call Pipy. This is a built-in function to generate a new configuration. Now I call listen on that configuration object to add a pipeline layout to my configuration that starts listening on port 8080. That means when the connection is accepted, a pipeline will be created to handle it. The pipeline will be created based on my pipeline layout. Now listen gives me the same configuration object so I can chain function calls on it. The next function we call is serve HTTP. That's to add a serve HTTP filter to the filter layout we just added. Here's the pipeline layout we just created. When the request comes, a pipeline is created. It has only one filter inside. The filter decodes the request and calls our script function. The function outputs a response. The response is encoded by the filter and then goes out from the end of the pipeline. Now if I curl the port, we can see it's working. We don't have to always write one-liners on the terminal to use Pipy. We can write more complex scripts in files. If I start Pipy with no command line options, it will start in repo mode, where we can edit code bases for our project and also debug it. The second example I'll show you is a proxy server. Again, we'll call Pipy first to generate a configuration. On that configuration, we call listen on port 8000. Now after that, we won't call serve HTTP this time. We'll instead call debug HTTP. This filter decodes HTTP requests just like serve HTTP, but instead of giving that request to a script function, it gives it to a newly created subpipeline and let the subpipeline handle the request. Now we define the subpipeline layout, which means to tell Pipy what filters are on it. Since we'll forward the incoming request to the upstream server, we use mux-HTTP to put that request in the queue. But many requests are coming at the same time. There will be many mux-HTTP filters to handle them. All these mux-HTTP filters will put their requests in the same queue to make up a shared stream. In Pipy, all streams run in pipelines, so we define a second subpipeline layout for that shared stream. Now on this pipeline, we'll have only one connect filter to send that stream to the upstream server. Now we can start the script right from the Pipy repo. We also need an upstream server. Pipy repo comes with a few sample scripts that we can use. So we open one of them and copy the URL from the browser and start a second Pipy instance pointing to that URL. Now we have two servers running. If I test it, it should work like that. The third example I'll show you is routing requests to different servers. We'll make changes on top of our previous example. First, we wrap our entire script inside the function, so we can use the function's arguments as global variables. We create a URL router to map a couple URLs to different server addresses. Now we define a context variable for the calculated target server address. And then after request is demux, before going to muxccp, we calculate the target where it goes to. We can do this in a handle message starts filter with a script function. Function will be called every time a request header is received. The header information will be given to the function as argument. We calculate target in this function from the requested path. After that, we need a branch. When the target is found, we forward the request by muxccp as we did before. Otherwise, we start another subpipeline. In that subpipeline, we replace the request message with a 404 not found response. And that response will eventually go to the end of all pipelines and back to the client. Now test it. It works. The last example I'll show you is load balancing. This time we will change the URL router to map paths to load balancers. We knew a round-robin load balancer with a list of targets. After this change, what we get from the routing calculation will become a load balancer object instead of the actual target address. To get a target address to connect to, we call next on this load balancer object. When load balancing, the target addresses will rotate. So if many muxccp filters are handling many different requests, you can only share upstream connections when the target is the same. So we give a target as the key to a specific subpipeline it puts the request in. Also, we give the actual target address to the connect filter. Now let's see how it works. The responses change for every request. That means the upstream servers are rotating. As you can see, what makes Pipy so powerful and flexible is its pipelines and filters. By combining the filters and writing custom scripts, there are endless possibilities to how we use Pipy. More importantly, this flexibility doesn't sacrifice any performance. In our benchmark, Pipy is substantially faster than other comparable products while consuming much less resources. In a general benchmark test, we see Pipy is able to handle the same amount of workload by using only half as much of memory and 60% of CPUs as Envoy proxy.